Hey friends, welcome back to the channel. This video is one of the videos in the Calculus Hours video series, and in this video we're going to talk about applications of definite integrals. Well, under this heading, we're going to learn to calculate the area beneath the curve using integration. We're also going to learn to calculate the volume formed by revolution of a certain curve using integration. In the volume of revolution, we're going to learn two different techniques. Number 1 is going to be the disk and washer, and number 2 is going to be the shell method. Then we're going to move on and discuss how we can calculate the surface area of the solid generated by the revolution. So let's get on with the video. So let's start with area under the curve. Well, before we get on with integration, let's first discuss how we can calculate the area of a rectangle like this one. Well, how can we do that? Let's consider this rectangle has length L and the width x. The area then would be L times x. This is the concept that we're going to use in determining the area under the curve. Okay, now let's consider you have a function graphed this way, and you need to calculate the area beneath this function, area bounded by the function and the x-axis between the limits a and b. That is, you need to calculate this area. Well, how are we going to do that? So the approach that we use here is we divide this area into many strips such that each strip has a width x. Since these strips are a very minute width, we write the width as dx. What happens is the length of the strip is going to be the value that the function returns at that particular point x. So it's going to be f of x. So what happens is the area of one strip is going to be f of x dot dx. However, since we want to calculate all of this area, we need to add all of those strips. So to calculate this total area, what we do is f of a dot dx dA plus f of x1 dx1 plus f of x2 dx2 plus f of x3 dx3 plus dot 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 till so on and so forth until you reach the point B. So basically what we're doing is we're dividing this area into many strips. Each strip has width that is very small. So technically, if we look at that strip, it is basically a line. So what we are doing is we're summing up all the areas of those strips to form the area of this region. And so we're going to write it in this way. However, integration makes things easier for us. Well, integration helps us divide the region between A and B into infinite amount of strips, and it helps us reach the very minimum value of the width. And so the integration as f of x dot dx, meaning the length and the width of the rectangle for all the rectangles between A and B. And so this is going to return us the area. Well, this is the logic behind the area under the curve and why we calculate it using integration. Well, now let's see an example of a curve that is somewhat like. What we need to do is we need to calculate this area. Well, we'll first calculate this area between these 2 points, and then we are going to subtract from it this area to get the green area. And so the green area is equal to the area bounded by the curve is going to be equal to the area bounded by the curve f of x. That is integration of f of x dot dx minus the area bounded by the curve g of x. That is the blue curve. So integration of g of x dot dx. Well, with that said, ladies and gentlemen, let's go on and discuss volume of revolution. So in the area beneath the curve, what we did was we divided the area into a certain number of rectangles such that the width of the rectangle was very minute. And then we added all those areas of the rectangles rewrote them in the form of integration, and hence discovered the area in the form of integration. Now what we're going to do is we're going to do the similar thing with the volume. We're going to take the cross section rather than a 2D rectangle. Let's see what this means. Consider you have a curve like this between A and B. And what you need to do is you need to revolve the area bounded by the curve and the x-axis around the x-axis. So like this. So this is going to result into a solid forming somewhat like this. So we need to calculate the volume of this solid. So to understand this, we need to understand how a volume of a cylinder is calculated. Well, let's consider you have a cylinder such as this with a radius r and height h. What happens is you write its volume as pi r square h. So now let's consider, so the cylinder is basically the result of revolving this particular line around the x-axis 360 degrees. So what happens is, let's consider you have the equation of the line being f of x. So in this case, we can rewrite r as f of x, where f of x is the equation of this line. And so we can rewrite the formula for volume as pi f of x squared h, where h is the difference between the final and initial limit. So let's apply this onto a curve. Consider we have this curve. We want to revolve this area between A and B around the x-axis. So what we do is we divide this into segments having height or width very small, that is dx. And so what we do is we consider these segments to be revolving around the x-axis, and hence when they revolve around the x-axis, they generate a cylinder. And the cylinder is a cylinder having height dx, that is a very small height. So how can we calculate the volume of the cylinder? Well, consider this particular cylinder. So how can we calculate its volume? Consider you have this width very small, so the final initial lines are going to be overlapping. So both of the lines are going to represent approximately the same point x. We substitute that value of x into the function's equation and hence the function returns a value that is f of x. So what we have is now we have this particular height, that is the f of x, as the radius. Well, how can we calculate the volume generated when we revolve this particular segment around the x-axis? So we get radius to be f of x and the height of the cylinder to be d of x. So what happens is the volume is going to be pi f of x squared dot d of x, that is pi r square h. And so what we do is between the limits a and b, we make many such cylinders having a very minute height, and we add their volumes up, so forming the total volume, and hence we get the volume between A and B formed by the revolution. So what we do is, until we reach the point B, because integration helps us divide the segments between A and B into very minute segments, and hence sum them all up by substituting them in the function we provide in the integration symbol. So what happens is, if we write here pi f of x squared dot dx, it's going to return the same thing. Hence, our volume of revolution of a function around the x-axis is going to be written as ba pi f of x squared dot dx, where f of x is the radius of the cylinder, and d of x is the width of the cylinder, which is very minute. Hence, we make the cylinders using each and every segment that lies between A and B of very minute width, we revolve those segments around the x-axis forming cylinders, and hence we add the volume of those cylinders to form the final volume. Similar case is going to be with when we revolve a thing about the y-axis. So basically in this case, the radius that you're going to get is going to be f of y, and the limits are going to be the y-axis ones. So you're going to integrate b to a pi of radius squared, that is f of y squared, dot dy, because the width is on the y-axis, so dot dy. Now let's talk about what are we going to do if we have the following configuration. Let's consider you have this function, let's call it f of x. Let's consider you have this function, let's call it g of x. And you need to calculate the volume generated when this area is rotated about the x-axis. What it basically is a solid of this form, a hollow solid. So what we can do is we can basically calculate the volume generated when f of x is revolved around the x-axis between the two limits, and we can calculate the volume generated when g of x is revolved around the x-axis between the two limits. Subtracting those two volumes is going to result in the volume generated when this portion is revolved around the x-axis, the pink one. Well, to generate the volume after revolving g of x around the x-axis, we're going to get integration from b to a, where b is this point, a is this point, pi g of x squared dot dx, and the volume generated when f of x is revolved around the x-axis is going to be from b to a, f of x pi f of x squared dot dx. Well, and so the pink volume, this particular volume, when this particular area revolves around the x-axis, the volume generated is going to be the difference of the curve that dominates and the curve that is below the curve that dominates. So what happens is we subtract the volume generated by g of x from the f of x, that is pi f of x squared dot dx minus pi g of x squared dot dx. So hence we're going to get the volume when this portion is revolved around the x-axis, that is this volume. So what we did was we calculated the volume of all of this cylinder, and then we removed from it the hollow part, the volume of the hollow part. Similar to the case where we have a cylinder that is hollow, like this, and we need to calculate all of this volume. So what we do is we calculate the volume of cylinder 1 and subtract from it the volume of cylinder 2. So this is what we've done here. We also refer to this method as the disc and washer method. As far as you know, the logic that is happening over here, that is dividing the region between the limits into segments, revolving the segments around the x-axis, determining their volume, and adding that all up. So until you know the logic of it, it's going to be very easy for you. Well, now let's discuss a very important example of it. Consider you have a curve like this. The area between this curve and the x-axis between a and b was revolved around the x-axis. Earlier on, we discussed the volume generated by that revolution. Now what we're going to discuss is something different. Well, now what we have is, we have a line, that is y equals f of x. Let's call this function as g of x. So now what we have here is, we have a line y equals f of x. And what we want to do is, we want to revolve this curve around this line. So, and we want to calculate the volume generated by this revolution. So what happens is, when you revolve around the line, when you revolve this curve around the line y equals f of x, what you get Well, what happened was when you revolve this function around the line y equals f of x, you get a solid that is something like this, where this is the line y equals f of x. So over here, what you need to know is the radius. Well, if we divide this volume into cylinders of very small width, what happens is we can specify its radius. So how are we going to specify its radius? Well, since the solid is going to revolve around the line y equals f of x, this is going to be our radius, the line between g of x and f of x at any particular x. So what happens is this is our radius. How are we going to calculate it? Well, earlier on we said that the radius was the value our function returned at that point, that is g of x, but that is basically this particular radius. This is g of x. However, this particular length is f of x. So to calculate the radius, you're gonna have to do g of x minus f of x. Now when you've gotten the radius, you just need to put on an integral sign and substitute in the values. So the volume of revolution is gonna be b to a pi times radius squared. Now the radius you have is g of x minus f of x dot dx, where dx is the width of the minute segments that we've made. So what this function does is it divides the area between a and b into many segments, and then calculates the value of g of x at every segment, subtracts from it the value of f of x at that particular segment to get the radius of that segment. Then it squares it, multiplies it with the width, and then adds it into results of the preceding segments. Hence our final volume is going to be this. Well, what happens if you revolve this function around a line that is parallel to y? Not a significant difference. Well, now you have this thing as f of y, this thing as g of y. And so the radius is going to be f of y minus g of y, and the limits are going to be b to a, that are these particular limits on the y-axis, and the width is going to be this, that is dy, because it's on the y-axis. So our final result is going to be f of y minus g of y whole square dot dy. All of this was an example when your curve is being revolved around a particular line. And up above we discussed when the curve was revolving around the axis. Before that we discussed the area bounded by the curve. So we're done. We're basically done with the area. We're done with the volume of revolution, disk and washer method. Let's move on to the shell method. Now, let's consider you have this curve, you have the area between A and B, this area. Now what we discussed earlier on was that this area was being revolved around the x-axis. Now what happens is, well, there is a possibility that in a question you are asked to revolve this area around the y-axis. How are we going to do that? Well, we cannot define a particular r over here because there are two different r's, right? There are two different r's. So for this, we're going to consider an example of a cylinder again. Let's consider you have this cylinder that is hollow from inside. The radius of the larger cylinder is r1 and the radius of the smaller cylinder is r2. So the volume of the blue solid, that is the volume of this cylinder, is going to be pi times r1 square, consider the height h, minus pi times r2 squared dot h. Well, we're going to rewrite this as pi h r1 squared minus r2 squared. rewriting this again, we have r1 plus r2 times r1 minus r2 using the difference of square identity. Now, if we multiply and divide this by 2, well, let's see what we get here. So 2 pi h, rewriting it, we get r1 plus r2 over 2 times r1 minus r2. And hence what we get is 2 pi times average radius times the thickness. That is the thickness of this area. r1 minus r2 is thickness. So the thickness of the generated solid. So now all of this is equal to the volume of the cylinder. So now what we can do is, we can consider the cylinder to be centered like this, where this green line is our f of x. So doesn't this form a similar case? Well, you have this area and you need to revolve it around the y-axis, and you have something hollow too. So now let's talk about it in a bit detail to make it more clear using this diagram. So what happens is, as usual, you divide this area into many segments. Let's consider this as one of the segments. And what you need to do is, you need to revolve this around the y-axis. Well, what you do is, you make those segments, and then you consider all of those segments revolving around the y-axis, and you generate the volume. You calculate the volume generated by each of that segment, and then you sum them all up. That we do by integration. That is, the integration helps us determine whatever you want to calculate on each of the particular x, on each of the particular value of x, and sum them up. So integration helps us sum things up. However, so what happens is, well, we divided these into segments, and we consider, now what we do is we consider each of those segments revolving around the y-axis, and we consider the volume generated by each of those segments revolving around the y-axis, and we sum all of those volumes up. That is, the volumes generated by each of those segments. So let's consider this particular segment. So what happens is, this radius is going to be r1, and this radius is going to be r2. Now r2 minus r1 is going to be its thickness, that is the change in x. And since we are considering those segments to have a very, very minute width, we're going to consider it as dx. Right. So we're done with the thickness part. Now, let's try and get the average radius. So since change in x, that is the width of the rectangle, is very minute, we consider r1 and r2 to be overlapping with each other. That is, we consider r1 to be approximately equal to r2 because they have very minute width. That is, a width that approaches to 0. Hence, the final and initial radii overlap. And what happens is, you get the average radius as r1 plus r2 over 2 to be equal to 2 times r1 over 2 equal to r1. That is the value of x at that particular segment. So you have the average radius as x. Now what's the other thing that we want to calculate? The height. Well, what is the height over here? Height is f of x. Right? Well, so the height is f of x. So what we do is, the height is f of x. Because if we compare this, the height is h. And comparing it with this thing, the height is going to be f of x. of each particular segment. So what happens is, now we substitute these values into our volume formula. So the volume of one particular segment, the volume of one particular segment being revolved around the x-axis is gonna be 2 pi, replacing h with f of x, replacing average radius with x, and replacing the thickness with dx. So this is going to be the volume of one particular segment at any point x. Now to calculate the volumes of the segments, volumes generated by revolving the segments at every particular point x and then summing them all up, we're going to do this by integration from a to b. That is, what it does is, it calculates the volumes of each and every segment that lies between each and every segment at the value of x that lies between a and b. So what this does is, it calculates the volume formed by rotating the segments at the particular x between a and b and sums them all up. So 2 pi f of x1 dx1 plus dot the 2 pi f of x2 dx2 and dot. So what this integration symbol does is, it sums them all up. It calculates the volume, that is, it substitutes the value of x between a and b, each and every particular value of x between a and b, into the function f of x, puts it here, and then sums it all up. Hence what you get is finally 2 pi f of x dot dx, where f of x is the height, x is the radius, x is the average radius, and dx is the thickness, where f of x is the height, x is the average radius. Since both the radius approach each other in the segment, because the width is very minute, and d of x represents the width, that is the thickness. So let's do an example of this right here. Question 1. Consider you have a function y equals x squared between 1 and 2, and you need to revolve this area between 1 and 2 around the y-axis. So, since this is, how are you gonna recognize whether you want to apply the shell method or the distant washer method? So you need to use the shell method when you have different axes, that is, rotation about axis 1 and area bounded by axis 2. So now, how are we going to calculate this? Well, we're going to use the shell method, and for shell we need to determine, what we do is, we need to determine r2 minus r1, that is the width, and that is dx, because this is dx. The other thing that we want to determine is the average radius. Average radius is going to be equal to x, because at each and every point of x between 1 and 2. Because we have the x-axis, and r1 plus r1 really approaches to r2, and so 2 times r2 over 2 is going to be r2, that is the value of x. What else do we need? We need the height, and height is f of x, that is x squared at any particular x, at that particular x where we're finding the radius. Height is equal to f of x, that is x squared. Now let's substitute things into our formula. We have integration from b to a to b, 2 pi. What we have? We have average radius, that is x. We have height, that is x squared. And we have the thickness. Now integrating this is gonna form, let's substitute the limits as well. What we have is 2 pi x4 over 4 from 2 to 1. So this is going to result in 15 pi by 2. Well, let's consider one more example over here. You have a curve y equals under root 4 minus x squared and the line y equals x. And you need to revolve this particular area around the y-axis. Well, how are we going to do that? Well, what we can do is, we can divide this into segments. Each segment has the width dx. Let's consider this y1 and then y2. So each segment has the height f of y2 minus f of y1, because height is this minus this. This is going to be the height. And what is going to be the average radius? Well, the average radius is going to be x. So let's apply the shell method from this point to this point. So what is going to be this point? A. Let's consider it A. So A is going to be the point of intersection of y equals x and y equals under root 4 minus x squared. So x squared equals 4 minus x squared, so 2x squared equals 4, x squared equals plus minus under root 2. Well, since this is a positive x-axis, we're going to consider a equals under root 2. So from under root 2 to 0, we need to use the shell method. So we use 2 times pi. Well, there is one more option that we can calculate this volume, and we're going to talk about it later on. But let's first consider using the shell method, because it's pretty easy. So 2 pi times, what is going to be the h? Height is going to be f of y2, that is 4 minus x squared under root minus f of y1, that is x. This is the height. And what is the average radius? Well, the average radius is x. And what is the width? Width is dx. Integrating this particular expression is going to get us to the volume of revolution. Well, now consider the option number 2. The option number 2 was revolve this around the y-axis. So why didn't we just do it using the simple thing? Well, let's talk about first why that was difficult. Well, you can see that from the point, let's consider this point is A, right? The intersection. So what we saw here was from 0 to A, this area was only bounded by this line, right? And the area from A to 2 was only bounded by the curve. So yes, we could have calculated the volume in the general way, but for that we would then have to divide all of the area into 2 different regions. Let's do it over here. So we first need to define this region and then this region. So the first region is from 0 to A, where the radius is f of y, that is y equals x. So f of y is gonna be y. So the radius is gonna be this thing, and using the general method, we're gonna use pi times f of y squared dot dy from 0 to A only. Now for this region, we're gonna do from A to 2. Well, we had the equation of the curve being y equals 4 minus x squared, and so f of y is gonna be, this was f of x, so f of y is gonna be y squared minus 4 equals negative x squared. So f of y is gonna be under root of 4 minus y squared. And so we need to integrate from A to 2 pi times 4 minus y squared whole squared, because this is f of y squared dot dy. Adding these two up, that is the volume generated by revolving this area and this area, adding those two volumes up is going to result in the volume generated by all the solid. So now I want you to do an experiment by yourself, and so what I need you guys to do is calculate this integral and then calculate this integral? Well, you need to calculate the a here first. What is a? Well, a is the intersection, the y coordinate of the intersection. We knew the x coordinate as under root 2. Now let's and we have the line y equals x. Let's substitute x in place of under root 2 in place of x, and so we're gonna get y equals under root 2 and plus minus under root 2. And since a is on the positive y-axis, we know that the a is under root 2. So now I need you to calculate this integral all by itself, and then what I need you to do is calculate this integral all by itself. And so what I want you to do is verify that these two are equal. Well, you need to substitute f of y here. What is the f of y over here? From 0 to a, the area is bounded by the line, so f of y is y. So you're going to replace this by y. Yeah, so this is using the shell method, and this is using the general method that we discussed earlier on.